Okay, so we're talking about the universal law of gravity. Apologize, today I have to look at my lecture notes from my phone because over the weekend the desktop, my computer is not printing anything. So if you see me looking at my phone, I'm not like chatting with somebody in the middle of lecture. I'm just looking at my lecture notes. Okay. Okay, so we're talking about Newton's law of gravitation. All right. So this is kind of a profound thing. As far as I know, the story is actually real about Newton seeing an apple fall and asking, why did it fall? One of these questions that humans had sort of ignored for many thousands, hundreds of thousands of years perhaps, and nobody figured out exactly why it fell. So the question was, what made the apple fall? And the fact that everything seems to fall suggested there was something universal. So Newton came up with this universal law of gravitation. So if you have an object, so let's make it a spherical object. Okay, let's say it has a mass m1. And then if you have a mass here, m2. And now if I go from the centers of these masses, okay, so I'll make them nice spherical objects so it's not complicated. And I measure the distance between the centers of these spheres. And let's say that distance is r between them. Then there's going to be an attractive force going like this, F, in this direction. And then there'll be another force going in the opposite direction that pulls them together. Okay? So I think I've said this before. You are sitting next to your neighbor, and you are pulling on your neighbor with an attractive force. And your neighbor's pulling on you also. So if you were to wait if there was no friction in your seat, you're sitting on a frictional surface, after a very long time, you would actually be stuck together. Okay? So think about that. So this is the law of gravitation. The gravitational force for the masses, m1 and m2, the gravitational force for masses m1 and m2 with radius, or no, radius is a very bad term, with separation. Radius would be very confusing. With separation distance, r, as magnitude, and I'll write it as magnitude of F is equal to capital G m1 times m2 divided by r squared. Okay? So to be precise, r is the distance between the centers of the mass m1 and m2. Okay. Now, what is this capital G? Okay, yeah, it's a gravitational constant. It's the universal constant of gravitation. Newton's constant, sometimes called. It's 6.67 times 10 to the negative 11th. So it's really small. The units are newtons times meters squared divided by kilograms squared. And this is the universal gravitation constant. Okay. Any questions about this? So that's the magnitude. The direction is already shown in the diagram. They just attract each other. So the force is attractive. And if you want to be very specific, the direction is just simply you have M1 and then you have M2. There's a line between them, the centers. Okay, so the direction of the force is along a line. Direction is attractive along a line connecting the two masses. Is that clear to everybody? You just make a straight line between and they each other. The same strength. Yeah. That's right. So this F is what this one feels. There's another F, like what this one feels, just like a rope. You pull on each one. Okay. All right. So as I said, the 6.67 times 10 to the minus 11, this is a really small number. So unless you have, 10 to the millions of kilograms or something, you don't really feel much of a force at all. Okay? But the Earth is huge. Has a lot of mass, and so that's why you feel the force of gravity from the Earth pulling you to the center of the Earth. Okay? So that's the way to think about it. The Earth, you try to find where the center is pretty much straight down from wherever you stand. No matter where you are on Earth, you're standing straight up. The center of the Earth is straight down. So that's the way gravity is pulling you. Okay. All right. Now, so what we can do is we can actually derive the force of gravity on the surface of the Earth. So we already know the force of gravity on the surface of the Earth is, the weight is m times small g, where small g is 9.8. 9.8 meters per second squared. And so let's derive that from what we know about the Earth. Okay. So let's talk about the Earth. And so we have, all right, the Earth here. Okay, that was supposed to be spherical. I sort of messed that up. And we have a mass there. Okay, it doesn't need to be at the North Pole. It just, people like to visualize things when it's, it would still work this way, but somehow that bothers people. Okay, so I'll just put it on top of the Earth like this. Okay. And so now here's the center of the Earth. And the Earth has a mass, let's just call it ME for Earth. And let's say the radius of Earth will be this distance, RE. And let's say this mass, let's say, is M, plain old M. Okay. So it's sitting somewhere on the surface of the Earth. Then we know that there's going to be an attraction between this object here and the center of the Earth. And the Earth, pointing towards the center of the Earth. There'll be some force F. Okay. The gravitational force. Let's calculate what the force will be. So let's first give you some numbers. The radius of the Earth, if you average over all points on the surface of the Earth, it's approximately 6.38 times 10 to the 6 meters, 10 to the third kilometers, if you like. The mass of the Earth by the way, I'm giving you the mass of the Earth, but you could actually do this calculation I'm doing backwards, and you could deduce the mass of the Earth, because most of you probably wouldn't know how to calculate the mass of the Earth. There are, by the way, there are tricks to figuring out the radius of the Earth by actually looking at the sunset, for example, at different times of the day, from different. Well, just looking at the sunset and figuring out the angles and measuring geometry, you can sort of estimate the radius of the Earth. So if you knew the radius of the Earth and you can measure the acceleration on the surface of the Earth, you can actually calculate the mass of the Earth. So doing this calculation backwards. But let's just do it straightforwardly going forward. So let's take the mass of the Earth as 5.98 times 10 to the 24. Kilograms. All right. So then let's calculate the gravitational force. It will be F is equal to capital G times the product of the two masses. Okay. So the mass of the object, small m, times the mass of the Earth, okay, divided by the distance between the centers squared, RE squared. Everybody's agree on this? Okay. Then we have G is 6.67 times 10 to the negative 11. And then we have for the mass, okay, I'm running out of space here. Let me do it on a new line here. 6.67 times 10 to the negative 11 for capital G. And then for the small mass, okay, so this one we'll just keep it as M. Okay. Because I didn't give you a number, I just called it M, right? And for the mass of the Earth, I have 5.98 times 10 to the 24. And then for the radius of the Earth, I said 6.38 times 10 to the 6th. So I've done everything in standard SI units. And then I have to square it for the R squared. Okay, I plug in the numbers. If you don't trust me, you can do it yourself and check math. It really comes out to m is 9.80 times 9.80. Okay. And if you're putting in the units, meters per second squared. So this is not m for meters, but this is m for mass. Okay, so 9.8, small g is 9.8. You can derive it from the mass of the Earth, radius of the Earth, and Newton's universal gravitational constant. Any questions about this? Pretty good. All right. So we've derived that. So we've derived that small g is equal to 9.8 meters per second squared. Now, let's consider what would happen if we had a more general planet. Okay? So suppose we're on Jupiter. Yeah, I mean, it's a real question you could ask. So let's say we're on Mars and we're standing there. We want to know how much we weigh on Mars. Or the Moon. That would be another option. So let's consider general planet. General planet. Let's call it, well, I don't need to give it a name. It's a general planet with mass m for MP planet and radius RP. And then we have, we do the same calculation. We put an object of mass m on the surface of the planet with mass mp and a radius rp, then we get that the force of gravity on planet P would be, again, the same universal gravitational constant. And then we have mp. Well, okay, I did it in the other order. So it's m times mp divided by rp squared. Okay. Questions so far? All right, now let's try to rewrite it the way we did it before. Remember, we had the small m out in front and everything else tagging along behind. So I can write this as small m times capital G mp over rp squared. Okay. Questions about this? So then the acceleration, the gravitational acceleration on the surface of planet P is going to be, let's call it GP, is going to be this thing here. Okay, capital G mp, mass of the planet, divided by rp squared, radius of the planet squared. Any questions about this? All right, let's try a quicker question based on this. Here. This is the question. Okay, so we have a planet. Let me a little bit. Okay, planet X has a radius that is twice the radius of Earth and a mass that is 8 times the mass of Earth. Okay? How much does a 1 kilogram object weigh on planet X? I'll open up polling. So you can start off by calculating how much it weighs on Earth first, and then try to get it to planet X. is Newton's law of gravitation. So Einstein came along in the early 1900s and said that the reason that Newton's laws actually work is because the mass actually deforms space and time. It's sort of like when you have it's like when you sit on your bed, you deform the mattress, and you can think of deforming the mattress would then make a tennis ball roll towards you. It's the same sort of idea. Something sits on a surface, it indents it, and other objects are attracted to it. The same idea with space and time. And so this was his general theory of relativity, where he incorporated the connection between space and time and gravity. So then one of the predictions that Einstein made was that if there's really this deformation of space and time, then if you made a violent sort of reaction, a collision or formation of a black hole, something, you would see oscillations in space and time. Okay. Now, this had not been observed. In fact, I think Einstein thought it was going to be too difficult to ever observe it. But over the last 20 or so years, they've worked very hard to make a gravitational detector. It's something called LIGO. It uses laser interferometry, where they actually look at the interference pattern that you get when you have a laser going down this way, going down this way, and then you look at the different fringe. We'll actually talk a little bit about interference later in this class. But they can measure actually deformations coming from a really small gravity wave. And they detected just a couple of years ago, 2016, the merger of two black holes. I guess, said what a black hole is. So a black hole is this object that, maybe 20 years ago when I was studying physics, sort of like you, I didn't really believe in black holes, but now it's clear that they exist. They are objects that have something called an event horizon. If you get too close and you go inside the event horizon, the pull of gravity is such that you can never escape. No matter what you did, you could never escape. Essentially, you'd be lost to everybody on the outside. But anyways, these are both these black holes, so as a result, you don't see any light coming out of the black hole. You don't see anything coming out of the black hole. You only can indirectly detect what it's doing by how it's affecting other objects around it. And so anyways, there were two black holes that had a merger in 2016, and this was observed, and that won the Nobel Prize actually last year. Not the most recent one, but the one before that. And then in 2017, actually August 17, they also detected the merger of two neutron stars, which are another exotic object. And so this is actually related to some of the work I do at EFTA, where the merger of the neutron stars are actually believed to be responsible for the formation of the heavier elements like gold and platinum and things like that. So there's indirect evidence that this merger of these two neutron stars actually produce a bunch of gold, a bunch of platinum. I'm talking about many times the mass of the Earth, so the mass of these precious metals. Okay. So anyways, I'm trying to tell you what you're learning is actually kind of cutting edge stuff, even though I'm teaching you the sort of the old-fashioned version. The modern version is very much in vogue these days. Okay. Now hopefully now you probably didn't click in because you're listening to what I said. Did everybody have a chance to respond? Okay, let's see what people said then. All right, a lot of people say D. Let's take a look. Let's see. Okay, so we just draw these pictures. By the way, whenever you have a problem where you have one case here, one case there, and you have to compare the two cases, like this, you have some setup of some, maybe a mass and a spring, and then you double the mass, double the spring constant. Okay, so in other words, you have an old setup, you have a new setup. One thing I recommend to students is you actually write down the cases separately with different symbols. Because I find that most of the time, very often, students try to use the same symbols for both of them, and they get completely confused because you get equations like r is equal to 2r, and then you're supposed to try to figure out what that's supposed to mean. Okay? So if you have one case and the other case, make sure you label them so that they're actually different. So here's Earth. I put E's for the Earth. Okay, so then the weight on Earth will be mg, small g, is capital G times m times me over re squared. Then I have the planet X, so I'll use the X for this case. And so I have Rx is the radius and mx is the mass. Then the weight on planet X will be g times mx over rx squared. Now, we are told that the mass mx is 8 times me, the mass of the Earth, and rx is equal to 2 times me. So now I'm going to try to play, the idea is I'm going to play around with wx so that I get something that looks like we with some extra factors out in front, and that will let me solve the problem. So wx is g mx divided by rx squared. Then I plug in mx is equal to 8 me, and I plug in rx is equal to 2 re, and that needs to be squared. And so this becomes, I have an 8 here, and I have a 4, or 2 squared, which is 4. So I get a factor of 2 mme over re squared. That's going to be 2 times the weight on Earth. But 2 times the weight on Earth is 2 times m small g. And the weight on Earth is 9.8, so it's 2 times 9.8, which is 19.6. Okay. Any questions about this? So you can do that? All right, very good. Then let's continue on. Okay, the next thing we'll talk about are going to be satellite orbits, or things that go around in a circular orbit. Okay, a satellite is just basically anything that goes around an object. Typically, when somebody says the word satellite, though, they mean an artificial object that we launched into space. But you can think of the moon as a satellite around the Earth if you want as well. Okay, so let's consider a satellite with mass small m orbiting the Earth. Let's make it the Earth, but we can switch it up and make it any planet. The formula that I write down can be changed for any planet or object orbiting the Earth in a circular orbit. Okay, with constant speed v and radius r. Now we're going to only consider circular orbits for the moment, but I should mention that in general you can have more elongated orbits. So, for example, everybody knows the story of Pluto. Yeah. Pluto was the 9th planet, and then it got demoted. It's now one of these almost planet things. Okay. It has a rather elongated, it's not a very circular orbit, it has a very elongated orbit. So the general orbit for a satellite is actually this shape, which is an ellipse. An ellipse is actually the figure you get when the sum of the distances to these 2 points, which is called the foci of the ellipse, is equal to a constant. So the total length of the string, which is the sum of the distances, is constant. If I put these at the same point, then I get a circular orbit. Right. Now, if you're interested in the history of planetary motion, then there's something called Kepler's laws. I'm actually not. I'm not covering it today. I will cover it later if I feel like that's something you'll be quizzed on. But Kepler's laws are about the general behavior of these more complicated elliptical orbits. There are some laws, like, for example, the amount of area that's swept out by this orbit is actually the rate of area swept out is actually constant in time. That's a consequence of angular momentum conservation, but we're not going to drive it. And then there's a relationship between the period of the orbit and the radius of the orbit. It's kind of a complicated formula, so I'm not going to get into it here. Okay. But we're going to consider the simpler case where the orbit is circular. Okay. Is everybody good on that? That's the simplest case. Typically, we like to make satellites go on circular orbits. So let's draw this. So I have here, this is obviously Earth. Well, I guess it's not obvious. I didn't draw the other stuff yet, so you don't know. Here's the center of the Earth. And I'm going to measure distances from the center of the Earth, because that makes it simple. And so I have then my satellite, and it has some speed v like this. Okay, and it goes around a circle. It's a big circle with radius r. And the mass of the Earth is me. Okay, so this is supposed to remind you of that example where I had a ball and I was doing this with a string, right? So this ball goes around a circle with a constant speed, and the string is pulling in. It's providing what we call the centripetal force needed to go around the circle with that radius r or with that speed v. Okay? Everybody remember that? Centripetal force, all that stuff. Okay. So, like a ball and a string, so we need to have some force pulling in, and we have a force. It's the force of gravity. So we're going to have gravity pulling in. Let's just say F gravity. So the gravitational force provides the needed net force. Okay. And this also comes by the name the centripetal force. And it has the value centripetal is equal to mv squared over r. Okay. Or if you want, it's also the net force. Remember, centripetal is not a new force. It's just simply the net force you need to go around a circle. So the gravitational force is that net force. There's no other forces in this problem. And so as a result, we can say that the force of gravity is equal to mv squared over r. So we have that force of gravity, okay, which is g m times me divided by r squared. This thing is going to be equal to this thing. They're equal to each other. Does that make sense? I need a net force of mv squared over r to go around a circle with that speed, with that radius. And gravity is the only force that matters here. I didn't talk about any other forces. That's the only one. So they'll be equal to each other, so we'll set them equal. I have, let's write it this way, mv squared over r is equal to capital Gm times me over r squared. Okay, let's try to simplify things. You'll note that the mass of the object doesn't matter, which is nice. So these guys can go away. Right. We have v squared over r equal to g me over r squared. It looks like we can cancel one of the factors of r. Let's multiply r to both sides. So then this goes away, and one of these goes away. So v squared is equal to capital G me over r. And then we take the square root, and we get that the speed is the square root of g times me over r. So that's the speed of the satellite. Okay. Any questions about this? So if you want to launch your own satellite, it sounds kind of cool. Yeah.
Would you be able to rewrite that as small g times r?
Yeah, you could try to. If you write in terms of small g, you will get the radius of the Earth coming into the problem. It makes it kind of ugly. Okay. All right. So yeah, if you're trying to launch a satellite, you need to know all these things. Obviously, if you're launching a satellite, you need to know tons of stuff. So you have to know exactly the orbit, whether you're going to hit other satellites, all that stuff. And you're going to have to figure out when it finally comes down that it's not going to crash somewhere and kill people. But one of the basic things is what is the speed of the satellite. Okay, now sometimes though they talk about the altitude of the satellite, and that's measured relative to the surface of the Earth. So that's just basically saying, all right, so I have some radius up here. Let me try to draw it like this. All right, so this is R. This whole thing is R. Okay. And then this piece here, thank you. And this piece here is the radius of the Earth. Okay. And then this piece is the remainder, which is called the altitude. So R is equal to the radius of the Earth plus the altitude. Hopefully that's obvious, right? It's just the extra amount you go beyond the surface of the Earth. This is obviously the radius of the Earth. And we were measuring small r from the center of the Earth. Any questions about this? All right. Now in my notes, I do this little song and dance repeating something we did before about accelerating frames. But we kind of already did this, so I don't think I need to do the whole thing. But I want to mention one thing. So you probably know, you've seen pictures of astronauts on a space station, right? And or maybe you've seen old footage of them on the space shuttle or some rocket. And you know that they're sort of like floating in space, and it's kind of cool. Okay? So they're weightless. And does anybody know why they're weightless? Yeah, that's exactly right. So the reason that the astronauts are weightless is not because gravity is really weak. So if you ask the average person on the street, why are the people on the space station not like feeling gravity? And they'll say it's because they're far away from the Earth. That's absolutely false. If you compare how high they are compared to the Earth, it's not really like this. It's actually more like they're kind of right here, right? They're really close to the Earth. So the actual strength of gravity, the gravitational force, is not that much smaller. It's just a little bit smaller. The reason why the astronauts feel like they're weightless is because they're going in a circle. They're going in a circle. And they have gravity's pulling down, and there's a net force. They're accelerating downwards, but they're in free fall. In other words, everything is doing the same thing. If I was in that orbit, and I just throw my pen here, it would just hang out with me and come with me with the same speed. Okay? In other words, it wouldn't fall. It would just glide along with me. Everything is accelerating towards the center of the Earth with this acceleration. So if I'm talking about the acceleration, it would be v squared over r without the m here. Okay? And because everything's accelerating like that, it's like free falling. It's just like when you're in an elevator and you just, somebody touches the cable, you just fall. It's the same feeling. Okay. That's why you're waiting. Questions about that? All right. That's all I had to say today. So I'll see you guys next time.